Hello and welcome to our lesson on wave theory. So today's goal, I want you to be able to explain wave theory, and I want you now to take from grade 11 the concepts of wave theory and move into explaining or using them with respect to the wave nature of light. So today, if you recall from grade 11, we talked about a wave is a vibration that transfers energy from one location to another. Now we have to extend this definition a little bit now because we have electromagnetic waves. So I'm going to add in here that an electromagnetic wave transfers energy through the use of magnetic and electric fields. So magnetic and electric fields. All right. So just a little bit of an extension. I'm not looking for regurgitation here. I'm just trying to step from grade 11 and tie it into our grade 12 concepts. So you have the note in front of you. There's three categories of waves. So we have our mechanical waves, and those are the ones we dealt with in grade 11, and they're governed by Newton's laws. So we have our angle of incidence equals angle of reflection. We have refraction properties, and all of them require a medium to travel. So our mechanical waves are ones you think of include our sound, for example, our water waves. They need to have that medium to transfer the energy. Okay. Then we move into some newer types, and this is the ones that we're kind of focusing on a little bit more. Electromagnetic waves are our third category here, and they are waves that don't need a medium. So this is how light gets from the sun to earth. It travels as an electromagnetic wave. It doesn't need a medium. Now, all electromagnetic waves travel, typo here, should be to the exponent 8. All right, just put that off to the side here. So the velocity should read 3 times 10 to the exponent 8 meters per second. And that's for all EM waves, electromagnetic waves, okay, in a vacuum. All right, so anytime they talk about light traveling through space, it's 3 times 10 to the 8th. And even it extends to, we assume it is that for air. Very, very rarely do we change it because it's such a minor change with respect to its velocity. So electromagnetic waves. So it includes your radio, your ultraviolet, your infrared, anything that uses that electromagnetic pulse. And the last one is matter waves, and that's a combination of particle and wave theory of energy and matter. So this is when you get into what's called quantum mechanics, and that extends beyond what I'm looking at in the grade 12 course. So there are your three major categories. So in order to be successful, we're going to take a step back. We're going to look at the different types of waves and review some of their key characteristics and properties. So just quickly going through this again is a review. So we have our transverse wave, and if I move from point A to B, the transverse wave would take on this shape here, kind of that sinusoidal graph we talked about. Key features again, we have our amplitude, and we have our crest and trough. So our crest and trough. And this again is particles moving perpendicular to the center line. So that means the energy is being passed along, and the particles are simply moving. They're simply moving up and down. So this particle here moved up at the center line. When this wave oscillates or fluctuates, it's going to move down. So the particle is simply moving up and down and not moving left to right. Okay, so it's kind of staying in that same location. Now longitudinal waves, trickiest ones for me to draw. So we have close lines spreading out, and then kind of going back into tight lines again. And we have our energy transfer. I'm going to have it heading that way. So the energy is being transferred by a series of compressions and rarefactions. So compression occurs where the waves or the particles are pushed together. So we have a compression. And where the particles have been spread apart, we call that a rarefaction. And they kind of align themselves with crests and troughs, same idea. So you can think of a compression as a crest, and you can think of a rarefaction as a corresponding trough. All right, just to help with that association between the two. And this is how sound travels. Okay, the first one, transverse waves, we're looking at water waves. Okay, water particles simply move up and down, whereas air, when we make sound, our longitudinal waves, our sound travels through a medium using a series of compressions and rarefactions, and that's what our voice box and our respiratory system will do. It compresses the air particles together and makes that energy pass through that series there. So the energy, just as a note here, is passed through particles moving parallel to the center line. All right. So our transverse waves are perpendicular, and our longitudinal waves are moving parallel. We had the examples in grade 11. I talked about the child swinging versus the spring oscillating with a mass on the end. All right, so as we move through, we talk about wave concepts now. I'm just going to briefly go over this. With the wave concepts, it kind of ties in some of your grade 11 and 12 math. So if I just quickly make an XY axis and create, let's go with a sine wave. All right. The equation, the reason we like transverse waves is so you can develop an equation for a transverse wave. And you have those skills from your grade 11 math course. Okay, so in general, I'm not going to go through all the cases. Y equals A sine K, and you might use different variables in your math courses. I think you use H and K, but I prefer the P and Q. So we end up with this transformed equation here. A for amplitude. A for amplitude. So for people that are kind of missing out on this, the A and amplitude starts with A. So they're kind of connected there, right? Yeah, you're rolling your eyes, but I know some of you didn't see it. Okay, so our K value. What's our K value? That's our horizontal stretch or compression. So horizontal stretch / compression. Okay, but that's really our frequency. It affects our frequency because if we compress it together, more waves are occurring, or more crests and more troughs are occurring, which means the frequency's increased. So our formula that we've used, and I'll use the degree formula here. So 360 divided by the period. Okay, for those that remember their radians, now are screaming out, no, make it stop. It is 2 pi over t. Okay, and that's how we calculate our compression or stretches. Now the next one, the P. P is for phase shift. Phase shift. And what I'm trying to get at there is that the reason I like using the P when we talk about our transformations is because in physics, P stands for phase shift. And for those that struggle like myself and didn't realize this till university, that phase doesn't start with an F, it actually starts with a P. Then we have phase shift. So there we are. So that's our phase shift, and you know that is our horizontal shift. Horizontal shift. And finally, we have Q, which is our vertical shift. And it doesn't get used very often. Our waves typically oscillate around the x-axis for the most part, and especially in the grade 12 course. So I got nothing for Q because I don't know many words that start with Q. And there we are. So a very quick review of all the concepts tied with that transverse wave. Now, I just want to go in and, if you can find a little bit of extra space here, just go over a couple other key ones that that I need to add in here. So our period, we typically use capital T for our period. That's time for one cycle. Time for one cycle. We have our frequency. And that is our number of cycles per second. Number of cycles per second. And please remember your units on here. So for period, it is in seconds. In frequency, we're measuring in terms of hertz. Okay? And our relationship between the two is that frequency is 1 divided by our period. So I'll put a red box around that one for you. And I just want to make some associations here for you and help you kind of make the connection with where we're going. So if I just talk about amplitude for 1 second, and again, small a, distance from crest / trough to center line. We made some associations, or we made some connections in the grade 11 course, and I just want to quickly revisit those. So, for example, amplitude. If we talk about it in terms of sound, which makes sense since that's what we did in grade 11. Make a little bit of a T-chart here. If I increase the amplitude in terms of sound, what happened to the sound? So if I increase my amplitude, hopefully some of you are saying, hey, it gets louder. If we increase our amplitude in terms of sound, okay, it gets louder, which means the reverse must be true. If I decrease my amplitude, it must get quieter. Now, if we tried to make that jump into light, what do you predict would happen in terms of light? So if we increase the amplitude of the light wave, okay, what happens? No hands, eh? Terribly disappointing. Okay, so if it gets louder in sound, then we would assume the connection would be brighter in terms of light, which means if we decrease the amplitude, it would then become dimmer. Okay, so there is your jump or connection when we move from the grade 11 course into our grade 12 course with light. Now, the other thing we analyzed or took a look at in the grade 11 class was our frequency. So if we increased or decreased the frequency, we said that what was affected was pitch. So if we increase the frequency, we would end up with higher pitch, which means the reverse is true when it comes to sound. What about light? What about light? What is the connection with light? So higher, if we increase the frequency, what happens? Well, the answer at this point in time, the prediction, what I've had in the past and traditionally what people say, is that it moves up the color spectrum. And that's not a bad answer at this point in time. Up the color spectrum. So that's what I've had in the past. And we're going to investigate this in more detail as we move through this particular unit. So it moves down the color spectrum. So if that was what your prediction was, you're right on what people are thinking. And some of you might actually be able to go a little bit further and talk about changing color and so on and so forth, moving to some maybe radio waves to maybe ultra high frequency, and that's fine. But that gives you a general connection between the two. So in the next video, we're going to continue moving along and kind of giving you just a general overview of what's involved, excuse me, in terms of light.